let's look at some examples to illustrate all of this stuff that we've been building. So I'm going to look at two kind of basic examples, a helix and a circle. Maybe we'll also comment what happens when we have a line. Okay, so first of all, let's start off with the helix, circular helix, 3 cosine t, 3 sine t, 4t. And let's go ahead and run through the computation of its TNB frame. So we have r prime is negative 3 sine t, 3 cosine t, and 4. All right, the length of r prime is the square root of 3 sine squared plus 9 sine squared, 9 cosine squared, and 16, which 9 sine squared plus 9 cosine squared is just 9. 9 plus 16 is 25. Square rooted is just 5. So the length of r prime is nice and simple. It's 5. So let's record, or maybe record that down below here. We'll have t is r prime over the length of r prime, and so that's 1/5, and because r prime has length 5, and r prime was minus 3 sine t, 3 cosine t, and 4. Okay, now let's go ahead and compute n. So to find n, we need to know what the derivative of t is. So I'm going to try to give myself some space for later. We'll scroll down here and write t prime is equal to, let's see, we have 1/5. We get negative 3 cosine of t, minus 3 sine of t, and 0. All right. So that you can factor negative 3/5 out, and you'd be left with cosine, sine, and 0. Well, if you take the length of that, that's just 3/5. And the reason being, the absolute value, obviously, of negative 3/5 is 3/5. And if you take the length of cosine, sine, 0, you just get cosine squared plus sine squared plus 0 squared, which is 1. Square root is just 1. Okay, so we end up with n, which is t prime normalized, is this negative 3/5 cosine sine 0 divided by 3/5. The 3/5 cancel out, and so you're just left with negative cosine of t, negative sine of t, and 0. Then finally, our binormal is the cross product of these two. So to finish out our TNB frame, B, imagine again we have our mnemonic, ijk across the top. We'll bring the 1/5 down. Remember the cross product is bilinear, so you can factor things out, and we'll factor out this 1/5. Now for the I component, we focus on the final two components, and we get 3 cosine of t times 0, which is 0, and then minus a negative 4 times sine t. That's just 4 sine t. The middle component, we ignore what's in the middle and just focus on the first and last components. And going down, we get 0, and going up, we get minus a negative 4 cosine t. So we end up with 4 cosine t, but wait a minute, it's the j component, it gets an extra minus sign. And then finally, the k component, we focus on the first two guys, and if we go ahead and multiply them out, we end up with a 3 sine squared minus a minus gives us a plus 3 cosine squared, but sine squared plus cosine squared is 1, and so that thing just simplifies to 3. So there you go. There's our TNB frame. Now, let's go ahead and look at acceleration. Okay, so our double prime, this is our second derivative, is negative 3 cosine t, and then minus 3 sine t, and 0. Remember that acceleration can be decomposed into tangential and normal components. Let's go ahead and figure out what those are. Now, if you remember the formulas for tangential and normal components, they involve not just a dot product, but also a cross product of the first two derivatives. So let's go ahead and compute the cross product of r prime and r double prime. Okay, again, the I component, we just focus on the final two components. So we get 3 minus a minus gives us plus 12 sine t. And then the j component, we have 0 minus minus gives us plus 12 cosine t, but it's j, so it gets an additional minus sign. And then the k component will end up with 9, because we'll have 9 sine squared minus a minus gives us plus 9 cosine squared. Sine squared plus cosine squared by the Pythagorean theorem, again, is just 1. So that collapses down to 9. By the way, eventually we'll want to have the length of the cross product. We need that not just for tangential normal components, but we also want that for curvature. Excuse me. And so let's go ahead and compute the length of the cross product. Okay, so that is well, we can notice we can factor a 3 out. Okay, and then we'll be left with 4 squared sine squared plus 4 squared cosine squared, plus 3 squared, which is 9. Right? So if we factor out a 3 from that, so we'd have 4 sine t squared is 16 sine squared, and then 3 factored out of the second component would leave us with negative 4 cosine t. That squared is 16 cosine squared t, and we have a 9. And so it looks like we have sine squared plus cosine squared as 1, so this is 16 plus 9, which is 25. Square rooted is 5. Long story short, the whole thing comes out to be 15. Okay? So, now, putting this together, we know that the tangential component of acceleration is r prime dot r double prime over the length of r prime. So if we compute the dot product, notice that r prime dot r double prime, you end up with 9 sine cosine and minus 9 sine cosine. Those cancel, and the final components, if you dot product them, you get 0. So it looks like the tangential component of acceleration for us is 0. Okay, we'll write that down as 0 over 5. The normal component of acceleration is the length of the cross product of the first two derivatives over the length of r prime, and that we've figured out as 15 for the length of the cross product, and we have the length of r prime is 5. 15 fifths is 3. So what do we have? We have that r double prime apparently is 0 copies of t plus 3 copies of n, and let's actually take a look at that. Does that fit with what we know? Well, look at what n is. N is minus cosine minus sine 0, whereas r double prime is exactly 3 times that. So that's something special about the circular helix. Okay, and of course, if we'd looked very carefully at the if we had looked more carefully at our what r double prime and what n are, we could have just gotten that without having to resort to our formulas. But I wanted to illustrate these things. Okay, how about curvature? Okay, we can go ahead and compute curvature. We have all the moving pieces we need. So curvature, take 1, is length of t prime over length of r prime. So if you've computed the TNB frame, along the way as you compute the TNB frame, you've computed length of r prime, and you've computed the length of t prime. And so, so if you've already computed those things, I lost my work. Oh no. So if you've already computed those things in the course of computing your TNB frame, you can just put them together and get curvature easily. right? So curvature for a helix is constant. This again makes sense. We think about how the curvature, a helix is shaped, and it's curved the same way at any 2 points. Okay, so if we wanted to write down a osculating circle, it would have an osculating circle at any point. If we drew some osculating circles at any point would have a radius of 25 thirds. Alternatively, you could compute curvature using our cross product formula, right? So curvature is the length of the cross product of the first two derivatives over r prime cubed, and so we calculated the length of the cross product of r prime cross r double prime is 15, and we know that r prime itself is 5, so we have 15 over 5 cubed, which again is 3/25. Okay, so if you ask which formula should you use, well, that depends, right? It very much depends on what you have already computed up to that point. If you already have the TNB frame, you should just put together length of t prime over length of r prime. On the other hand, I would say that generally, if you're computing curvature from scratch, this other formula is easier to use, but it depends. Okay. Finally, let's look at torsion. So I'm going to erase a little bit of our work here. Okay, get some things out of the way. All right. So for torsion, we need our triple prime, and that would be minus 3 sine t minus 3 cosine t, 0. And then we need to compute this triple scalar product, r prime cross r double prime dotted with r triple prime. And comparing our cross product and our triple prime, if we dot those, notice we end up with 36 sine squared plus 36 cosine squared plus 0. That looks to be 36. And then we're supposed to divide this by the length of the cross product of the first two derivatives squared, right? This will give us our torsion. And so we need to divide this by the length of the cross product squared, which we already found over here, right? That's 15. So this should be divided by 15 squared. So we have 36 over 15 squared. Notice that a 36 you can divide out a 9 from that, and you can get 2 3s divided out of 15. So if you simplify that, that's 4/25. So there's our torsion. So for this helix, we have that the curvature is constant and the torsion is constant, which again makes sense if you consider the shape of this thing. Okay, let's move on to our second example. So we'll insert a page. All right, how about for a circle? Okay. Let's just take a circle. How about a circle of radius 2? I don't know. I'll center it at the origin, and we'll pad it out with a 0. Okay. Well, so what do we get? Well, we have r prime is minus 2 sine t, 2 cosine t, 0. I'll skip a little bit of the detail, but the length of r prime clearly is 2. Just work that out. R double prime would be minus 2 cosine t, minus 2 sine t, 0. Okay, we'll eventually need the cross product of these two things. Let's go ahead and compute that. We get 0, right? Ignoring the middle column, for the j component, we'll get 0 minus 0, which is 0. Well, j component's negative 0. It's just 0. Okay, and then we have 4 sine squared plus 4 cosine squared, so the k component just comes out to be 4. By the way, the length of that, obviously, then is just 4, because it's 4 times the k vector. All right, what if we want the third derivative? Okay, the third derivative would be 2 sine minus 2 cosine 0. Notice if you take r prime cross r double prime dotted with r triple prime, we get 0. So in other words, the torsion for a circle is 0, but that's not surprising because a circle is a planar curve. That's what we should have. By the way, if we calculated curvature using our cross product formula, which is probably not the best formula to be using here, but oh well, we have 4 divided by 2 cubed. That's 1/2, which is not surprising because that's the reciprocal of the radius, right? So that's what we expected. How about the TNB frame? Let's do that. Well, maybe first we'll do the tangential and normal components of acceleration, right? So tangential component would be r dot r double prime over the length of r prime. You can see that if you dot these two guys here, you end up with 4 sine cosine minus 4 sine cosine 0. That's 0. And so the tangential component is 0. The normal component comes out to be 2. And so what we learn is that r double prime is no copies of the tangent and 2 copies of the normal vector. And that again would make very good sense if we think about how circles are shaped geometrically, that you are accelerating always towards the middle of the circle. If we start to draw this, you'd see there's t and here's n, right? The acceleration vector very much is pointing towards the middle, although n should be, if I was drawing this, I'm drawing more for like a unit circle. For circle of radius 2, n would be halfway pointing to the middle. Okay, so we've figured out curvature and torsion, tangential normal composed acceleration. Let's finish up with the TNB frame. So tangent is r prime normalized. Looking back up, what is r prime? We have minus sine cosine 0, right? We canceled off the 2 because we divided by the derivative, the length of the derivative. If we take the derivative of t, we then end up with minus cosine minus sine 0, and so its length is 1. By the way, there's a confirmation for curvature. Length of t prime over the length of r prime is 1/2. If we were asked to compute curvature for a circle, this is probably the easiest way to get at it with this formula, but it doesn't really matter. Okay, we got at it a different way. And so if we normalize, well, actually n and t prime are the same thing because the length of t prime is 1. So we just get minus cosine minus sine 0. Okay. And then finally, what is b? b is t cross n. If we compute the cross product, the I component is 0, the j component is 0, and the k component would be sine squared plus cosine squared, which is 1. It's the k vector. And that, again, isn't surprising because we have our circle that we're talking about here is a circle in the xy plane, and so which is also its osculating plane, and so the k vector is perpendicular to that. It's a planar curve, so the binormal is constant. That tells us that we have a planar curve, right? Constant binormal is the same thing as having a planar curve. All right, one last example as a bonus or extra punishment, however you want to look at it. Now let's look at lines. So any circular helix or circle in general will work very much like the examples we just did. Let's do lines though in general. So we have a point and then a direction vector times t. Well, first of all, what's r prime? R prime is just v. This is some particular vector, You'll put a sub-0 to say it's some fixed vector. R prime is whatever the length of that vector is. So our unit tangent is just v naught normalized. How about our unit normal? So we go ahead and compute t prime. Well, this is a constant vector here. So t prime is 0. N then does not exist. If you think about that, it makes pretty good sense, right? You're coming along a line. T is telling you what direction you're traveling along this line, right? T is the same everywhere. What's left? Well, there's lots of ways that we could define what n would be. That would be kind of a left-hand turn. So n isn't really well defined here. And so b is in the same boat. B does not exist. All right. How about, we'll go ahead and compute curvature while we're here, right? So curvature is the length of t prime over the length of r prime. And that's 0 over the length of... Oh, the curvature of a line is 0. Not surprising. Torsion is undefined, right? So we don't... From our setup, we don't have a way to define torsion because we have no normal vector, although really secretly torsion from a broader perspective is 0 because this thing is planar, right? If we are more careful with definitions, it would come out to be that. So for us, torsion is undefined according to some viewpoints. Other viewpoints, it's 0. If you want to use our formula, we have r prime is v naught, r double prime is 0. So the cross product of those guys is 0, and r triple prime is also 0. Anyway, if you use our formula for what the cross, what this is 0 over 0 doesn't exactly work out. But anyway, from a broader perspective, torsion really ought to be 0 for a line. So you want to be careful, right? If curvature hits 0, then you're not going to be able to define the normal at that point. So if you take, for instance, say sine or something like that, there will be points on sines anytime we have an inflection point where curvature will hit 0. At those particular points, you're not going to have a well-defined normal, right? So here's t and n. Here's t and n. But when you hit that point there, t is okay, but n, it's not clear whether the curve isn't sure whether it should send n this direction or the other direction. And so we'll typically just avoid worrying about those things.